Hi everyone, welcome back. This is Professor Herring. In this video, we're going to explore chemical bonding. Specifically, we're going to focus on ionic bonding, understanding how ionic bonds form, how to predict the strength of ionic bonds, and determining relative lattice energies. Read over the first 4 learning objectives to make sure that you understand the concepts that we'll be discussing. One of the first things we need to understand is something we've already talked about a little bit, and that's what's called the Octet Rule. And this is the idea that elements will tend to give up or gain electrons to obtain a noble gas electron configuration. When discussing the trends of the periodic table, we talked about how a given column will have all the elements within that column tend to have the same charge. And the reason for that is because they will either lose or gain those electrons in order to obtain that desired noble gas configuration. It ends up being more stable to have a completed shell. In the ebook, it goes into more detail about the symmetry of the orbitals, and if you're interested in learning more about that, then you can read up on that. But what we need to know is that the metals, the elements on the left side of the periodic table, will tend to lose electrons, whereas nonmetals tend to gain electrons. And here we also have represented for you a new type of notation. We call these the Lewis dot structures, and they indicate the number of valence electrons. Again, for the main group elements, which are the ones that are shown on the screen right now, their number of valence electrons is dependent upon which row that which column that they're in. And you can use that to predict the charge when they become ions and how they will bond with each other. There's 3 main types of bonding, and we're going to focus on the first 2. Ionic bonding is when we have opposite charges that interact. And we looked at this already in the previous chapter, but this is when metals and nonmetals interact with each other. The metals will lose the electrons to be cations. The nonmetals will gain electrons and become anions. Those anions and cations interact with each other to form strong ionic bonds. We also talked about molecules. Molecules exhibit covalent bonding, and this is when electrons are shared between the atoms. This happens with nonmetals bonding with other nonmetals. Examples of this include water, methane, and ammonia. And these compounds end up being less strongly bound than ionic compounds. They're softer. They melt or boil at lower temperatures than ionic compounds. The final type of bonding is what we call metallic bonding. And in this case, there is sharing of electrons, but there's not enough electrons to go around for each element to have a completed octet. And so the electrons flow as though they were in a sea in between the metals. And this is what causes metals to have high conductive properties. And so this usually is in the case of pure metals, something like calcium, lithium, copper, gold, etc., all the transition metals, or you can get combinations of metals where you have alloys, and those will exhibit metallic bonding as well. So let's do a check here and see if you can figure out what type of bonding would be present. So we want to know which of the following features both ionic and covalent bonding. Remember that in order to have ionic bonding, we need metals with nonmetals. For covalent bonding, we need nonmetals only. And so when we take a look at these and we evaluate, we can say, okay, potassium, this is a metal, bromine is a nonmetal. So this must have ionic bonding. Nitrogen is a nonmetal, as is hydrogen. That must mean that this has covalent bonding. Sulfur and fluorine are both nonmetals, and so this exhibits only covalent bonding. Hydrogen and chlorine are also only nonmetals, and therefore it exhibits only covalent bonding. And calcium carbonate is a little bit trickier for right now. It's a little bit more difficult, and that's because we haven't yet looked at Lewis structures. But what you want to recognize is that we have a metal, we have nonmetal, and nonmetal. And what this molecule looks like is the following. We have carbon, which is a nonmetal bound to other nonmetals, which means that this exhibits covalent bonding. And then you have calcium, and it's interacting with this group of nonmetals. And so we have a nonmetal interacting with a metal, and that exhibits ionic bonding. So the calcium carbonate is a little bit more difficult because you have both types of bonding present, and it's not necessarily obvious on first glance. One thing, however, that you are expected to know and to understand is what are the polyatomic ions. These are things like carbonate, nitrate, sulfate, etc. It's expected that you already know the polyatomic ions, and if you don't, please read over section 6 of chapter 6. All of these polyatomic ions are groups of nonmetals, and therefore they exhibit covalent bonding. However, because they are charged, when they interact with metals, you also get ionic bonding. And you will be expected to know that, and you will be assessed on this in the celebration of knowledge. All right, let's go a little bit more into ionic bond properties. So as we talked about just recently, ionic bonding is when electrons are traded to form separate ions. And ionic compounds consist of positive and negative ions, and it's a metal bound with a nonmetal. Some examples of this include sodium fluoride, potassium sulfate, magnesium nitrate, ammonium chloride. And they form what are called these lattices. And a lattice is a three-dimensional structure with repeating patterns. And so in this, what we see here is any one of these, we could say the cation is A, the anion is, actually let's do it the other way. Let's say that the cation is B and the anion is A. Now, why did I switch that right away here? Remember that when we have elements and they go to form the cation version, it gets smaller. When they become the anion version of that parent element, it gets larger. And just based on the sizing here, we're going to assume that A is the anion, and it's larger, and B is the cation. Some properties that you need to understand is that ionic compounds, they have very, very strong bonds. And therefore, they have very high melting and boiling points, and they're very brittle. So table salt, for example, is an example of an ionic compound. It's going to be solid at room temperature, and it melts at well above room temperature. Ionic bonding occurs, again, when ions combine to form the compounds. And so the electrons are donated from one element to the other. Sodium has one valence electron, and it donates its one electron to the chlorine, which has 7. In the end, they both end up then with a noble gas configuration. Sodium's noble gas configuration is neon when it's an ion, and the chlorine ion, also known as chloride, has a noble gas configuration of argon. And so this process is involved in forming ionic compounds. Now, if we take a look at the individual steps, you should recognize that taking sodium metal and forming sodium ion and releasing that electron is the ionization energy. Ionization energies are always positive, and chlorine gaining that electron you should recognize as the electron affinity. And in most cases, the electron affinity is negative. So if we were to quantify this process and see what's the energy involved, we see that it requires 147 kilojoules per mole to form these ions. And hopefully that makes sense. Well, hopefully it makes sense that it requires energy to break the bond between sodium, and it gives off energy to form the bond with chlorine. However, what we know from practical experience is that sodium chloride as a solid, an ionic solid, is very stable. And so if we were to take sodium metal and chlorine gas and convert them into sodium chloride, we see that this is an exothermic process. And so this raises the question of why is the formation of the solid so favorable if the formation of the ions themselves is so unfavorable? So this here, because it's endothermic, this is unfavorable. It requires energy to make that process happen, whereas the entire process as a whole is favorable. So how do we account for this difference? Well, the ionic bonding, the interaction between the ions, is favorable because there's a strong electrostatic interaction. And we've seen this before when we've talked about Coulomb's law. So this gets us to the idea of what we call lattice energy. And this is when it's the change in energy required when an ionic solid is separated into its ions in the gas phase. And that looks like the following. Take solid sodium chloride, you break it up into ions, and you convert it into a gas. And this requires a massive amount of energy. We call this the lattice energy. And differences in lattice energy can be explained using Coulomb's law. And we'll see some examples here shortly. Fundamentally, what you need to understand is that the higher the lattice energy, the more the ions are attracted to each other, and therefore the stronger the ionic bonds. The stronger the ionic bond, the higher the melting or the boiling point of that substance. So this value, this lattice energy, can be calculated using Coulomb's law. We're not going to expect you to calculate it, but to be able to compare by evaluating contrasting charges and the ionic radii. So let's take a look at what that might look like. Again, using Coulomb's law and evaluating the charge and the size, we can explain the differences in lattice energies. Take lithium chloride and strontium oxide, for example. When you combine the ionic radii of lithium with chloride, it's 257 picometers. The ionic radii of strontium oxide is 258 picometers. The difference between them is essentially nothing. There's practically no difference. On the scale of picometers, that difference is so small, you can't even tell the difference, essentially. However, the difference in their lattice energies is drastic. And the reason for that is because when you evaluate the charges, and if we were to plug those values into Coulomb's law, we can see that if we solve for some electrostatic potential energy for lithium chloride, because the charges on strontium and oxygen are twice that each, that's going to give us a lattice energy that's approximately 4 times the value of lithium chloride. And so we would expect strontium oxide to melt at a much, much higher temperature, to boil at a much, much higher temperature than lithium chloride. And so the point here is that the size does not matter as much. The charge is going to have a huge impact. And to kind of hit that point home, let's take a look at another set of elements. In this case, we have the chloride ion interacting with 3 different cations of different sizes. And so the ionic radii of this interaction differs substantially between the 3 sets. However, the charges do not. And so when we compare, you can look and see that the product of the charges in each case is equal. And the difference in the radii, while substantial, is on the order of 10 to 30% of each other. And what we see then is that the differences in the lattice energy are not that large. And because the ions themselves, if you look up the data on the periodic table in the ebook, you can compare and see that the ionic radii of a given ion does not change that drastically across the entire periodic table. You're not going to get orders of magnitude of 3 and 4 times the sizes. Therefore, just by virtue of the numbers themselves, the size of the ions does not impact the lattice energy to the same extent that the charges do. Excuse me. So, why don't you try this out as a practice problem? Pause the video now and work through this to see if you can solve this on your own. Welcome back. So, we want to rank these compounds in order of increasing lattice energy. So, a really easy way to do this is to draw out a table where you tabulate the charges, the relative sizes of the different species. And using the groups that they are in the periodic table, we can determine that aluminum and nitride would have a positive or a negative 3 charge. Sodium and chloride would have a positive and negative 1. Rubidium and iodide, a positive and negative 1. And a barium and sulfide are positive and negative 2. When we compare, because we know that the charge matters the most, we know off the bat that the aluminum nitride has the largest lattice energy, and barium sulfide also has a large, but not quite as large. And so we know that those two are going to be our the largest lattice energies. And at that point, what you could do is simply go over and find. And we see that we have 2 possible answer choices that fit those criteria of having aluminum nitride be the largest and the barium sulfide be the second largest. To compare between the other elements, we need to evaluate for the size. And the way that you want to do this is by always having a copy of the periodic table handy. Just doing a rough sketch here. If we place their locations on the periodic table, we see that, excuse me, let's try that again. Okay, so sodium, somewhere around here, whereas rubidium is 2 rows beneath it. We know that the atomic size increases as we go down. And so in terms of the size, we know that rubidium is larger than sodium. And then for chloride and iodide, chloride is above iodide, and so chloride is smaller than iodide ion. And so when looking at the pairs, since we have sodium chloride, that's going to have to be smaller than rubidium iodide. And so in terms of the lattice energies, sodium chloride is small, but rubidium iodide is smaller. And again, the reason for that is, take a look at Coulomb's law. They both have the same charge, but rubidium iodide is larger A larger distance means a smaller lattice energy. And so if we rank them, we can rank them that way, and we see that our answer is D. Now, if we compare this to the actual melting points, we see that indeed the melting point is correlated with the lattice energy. All right, why don't you try one more problem here before we finish off? Pause the video now and try this on your own. Welcome back. So we want to know which process is going to release the most energy. This is simple if you realize first that A and B are absorbing energy, as it requires energy to break any kind of bond. So we can't have A or B. C and D release energy because we're forming ionic bonds. And sodium fluoride's ionic bond is stronger than sodium chloride because the fluoride ion is smaller than the chloride ion. Again, when you take a look at their relative location on the periodic table, fluorine is above chlorine, and we know that the size increases as we go down the periodic table. And again, evaluating Coulomb's law, they have the same charge. Chlorine's interaction is a larger size, therefore a smaller energy of interaction. And so we know then that this is the strongest bond of the two, and because we're forming an interaction, it's going to release the most energy. That's it for this video. If you have questions about it, ask on Piazza, go to office hours, or go to recitation and ask there. Thanks for watching. Have a good day.